had here for y-axis. Right. Let me clean things up. We decided to go with this sectioning, so we have 3 segments, A, B, and C, which B is already gone. There you go. And we want to find the moment of inertia about y-axis, or area moment of inertia about y-axis for this composite area, which is composed of 3 rectangles. Right. Now, similar to what we did, I'm going to start. I'm going to look at each segment separately, find the area moment of inertia for each segment about y-axis for the general composite area, and then use those to find the area moment of inertia for the composite area about y-axis. Right? So starting with rectangle B, go with the same order. Rectangle B. Maybe I can bring the picture again here if I can find it. Just so I don't go back and forth, so you don't get a headache. Figure 13. There we go. Make it bigger. All right, so here are our segments. This one here and this one there. This is rectangle A. All right, then we have rectangle B and we have rectangle C there. Let's focus on rectangle A. This is A. I'm going to separate that. And here are the axes passing through centroid. It's exactly in the middle. X prime, Y prime. So to find the area moment of inertia about y-axis, right, we use the table we had here. We're focused on rectangle. We can find, we know the area moment of inertia about y-axis, which is I, Y prime, I bar, Y prime, meaning that moment of inertia about Y prime, that is the axis passing through the centroid. That's why we have the bar at the top. Is 1 over 12 B, H B cubed, B being width and H being height. Right? So I'll start with that, and then we use parallel axis theorem, knowing the area of the rectangle and the distance between these 2 parallel axes, which are going to be the distance between Y and Y prime. We can find the area moment of inertia about y-axis here. So I y is equal to I bar Y prime plus A dx squared, dx being the distance between Y bar and Y, right? The distance between these 2 parallel axes, this being dx. All we need to do is to identify the parameters correctly. All right. So Y prime bar, well, I know it's 1 over 12. How did I write it previously? 1 over 12 B. Oh, I'm doing it for rectangle A apparently. I called it B. I don't know why. Rectangle A. I wanted to go with the same order, but okay. Let's start with rectangle A. Some reason in my mind I started with A. All right. So it would be 1 over 12. B. What was that? We had B cubed H. All right. So or HB cubed. H V cubed plus A dx squared. Then these values would be 1 over 12. What is our H and what is our B, guys? We're looking at rectangle A, right? This one. So what is my H and what is my B for that rectangle?
Your height should be 300 and your base 100.
Exactly. Thank you. So H would be 300, all right, and B is 100 cubed. And as I said before, when you're calculating area moment of inertia or moment of inertia, and you're given the dimensions in whatever unit, is in millimeters, in centimeters, is in meter, you don't really get it in meter. Millimeters or centimeters, keep the unit in the same system. Do not go for converting into as like meter, let's say, because then these numbers are small. So if you convert it into meter, you're going to start rounding the numbers, and then you're going to lose accuracy. Since we are doing this calculation in the scale of millimeters, we need the accuracy to be in that scale. So don't convert things into meter. All right. So 300, 100 cubed plus the area, which is 300 times 100, right? And then dx, what is dx here, guys? Distance between y and y prime, right? We're using parallel axis theorem. So the distance area of the rectangle multiplied by the distance between two axes squared. Now, what is that distance?
Uh, 250.
250, exactly. Thank you, Tom. 250 squared. Away 250 squared, and I'll give you I y, and let me get the final number. The final number would be 1.9 times 10 to 9 mm4. Right? And let's call this IYA for rectangle A. We'll do it for rectangle B. Let's just do it for rectangle C, I guess, now that we're doing A first. So taking everything from here, rectangle A, we'll go to rectangle C right there. Right? And we put the coordinates here, right there. These are our centroidal, as they call it, axis passing through the center or centroid. How do I do it? ABC, right? Okay, I'm doing it. So IY for rectangle C is equal to I bar y prime plus a dx squared. Let's see where dx is. Dx is the distance between y and y bar. So here is you have your dx. This is your dx. It's a perpendicular distance. So again, 1 over 12 h b cubed plus a dx squared, 1 over 12 h is 300 times 100 cubed plus the area of C is the same as the area of A, is 300 times 100, and then the distance dx, and the distance is also the same. You have 600, C is in the middle of rectangle B, so that the distance from point C to one edge is 300, and then you have y prime, which is in the middle of rectangle B, so that's 50 millimeters from that edge. As a result, you have 250 millimeters from y to y prime. 250 squared. All right, and you'll get the let's see if I can squeeze in. IY would be all the same number, right? 1.9 times 10 to 9 mm4. That would be your IC. IA I see. And I'm gonna cheat, move everything up so I don't have to go to the next page. We have everything right here in front of us. It's easier. And then we'll do rectangle B. Right? And that's the rectangle B. Clean things up. This was the rectangle C. And then I'm gonna cut this from here. This would be a rectangle B. And the axes passing through the centroid are exactly the axes for the composite area. This is X prime, Y prime, right? So I, Y for B is basically I bar Y prime. I don't need any parallel axis theorem because these two axes are on top of each other, right? X, Y, and X prime, Y prime are exactly on top of each other. There is no distance, right? You can even try parallel axis theorem, then your dx would be 0, so nothing there. You can think about it this way. Right? But parallel axis theorem is used to find the moments about an axis parallel to the axis we know the moment about. Right? In this case, they are parallel, but they're on top of each other, so there isn't really no distance between them. So they are the same value in this table. Basically, is the axis we want to find the moment about, and the axis that we know the moment about are the same. This is our xy. So y prime is the same as iy. So that'll be 1 over 12 h b cubed, 1 over 12. In this case, we have our height is 100 millimeters for this rectangle, and we have our width as 600 millimeters cubed. You do this math, you'll get IY for B, you'll get that as 1.8 times 10 to 9 mm4. All right. So since the composite area or the composite cross, this composite cross section is formed by these three rectangles, the area moment of inertia or the moment of inertia for this composite area is the summation of moment of inertia for these three rectangles, right? There is no cutout, there is nothing else there. So all we need to do is that for the composite area, we get IY is equal to IYA plus IYB plus IYC that we calculated here, right, for A, B, and C. So you just add them up. You have two 1.9 times 10 to 9, and then you have 1.8 times 10 to 9 for rectangle B. Now you add them up, you add these three up, you'll get 5.6 times 10 to 9 mm4. This is your IY, right? Area moment of inertia about y-axis for this composite area. Now, what you can do as practice is do this, for your practice. Do segment this way. Call this segment A, or whatever you want to call it. If you're comfortable doing it, A, B, and C. Now you have three rectangles. One is A is 400 by 100. B is 400 by 100, and C is also 400 by 100. You have now 3 rectangles. Do this as practice. As practice, find the moment of inertia for this area by segmenting it into these 3 rectangles. Right? You should find the same thing, but it's a good practice because now you know the final answer, Ix and Iy for the composite area. So do this, segment this into these rectangles and find the area moment of inertia, Ix and Iy by finding the moments of inertia for each segment and summing them up.